Hi everyone. Today me and Aram will present one of the works that we do at Aerodynamics. I just want to mention that besides us there is a whole team behind this work, and we're just the ones who are presenting it to you. This will be the overall outline of the talk. We will first talk about the motivation why we're doing this, and then we will talk a bit technically about the task that we solve, and then at the end we will show some demonstrations and some experiments that we did, the results of the experiments. First, let's talk about the motivation, and I would like to ask a question. Do you notice anything strange in this picture? I will give you a few seconds to...
Something on the right side.
Something on the right side. No, that's a cliff.
Nobody is smiling.
Nobody's smiling, yeah, that's one point.
Where is the box?
Yeah, that's another point. The strange thing for us is that this guy is riding his bicycle with holding the bike with the right hand, and on the other hand he has a remote controller for the drone, and he basically does multitasking while he can enjoy the view, the cliffs, and everything else. So at Aerodynamics we are building a drone which is called sports videography drone, and it's meant to help this guy to solve this issue. So it's a small drone which can fit in your backpack, and while someone rides his bicycle and wants to have nice shots and stuff, he or she can relieve this, and it will follow the guy and will also record the video. These are some hardware specifications that are on this drone. This talk will be about the machine learning and AI stuff on this drone that we're doing on Raspberry Pi 4 and using Raspberry Pi camera version 2. It's not an event camera, it's an ordinary camera. I will pass the drone if anyone is interested to have a look, and if you have any detailed questions about the hardware, one of our engineers is also in this class. Ruben, please raise your hand if you have any questions, you can later approach him and ask. You can pass around if anyone is interested. Okay, and then I will let Aram speak about one of the tasks that we're solving on the Raspberry Pi.
So now I will talk about the overall object detection task, what is it meant to do, the general overview of it. Object detection is the task of identifying and localizing objects in an image or a video frame. It is used in a wide range of applications. For example, in autonomous cars, for detecting autonomous vehicles, for detecting cars, person, different other objects, in order to understand the environment and continue the driving. It is also used in surveillance cameras. For example, if cameras are put in streets, it can analyze the traffic and optimize it in order to have a better traffic. And also it is used in agriculture. It can be used in agriculture. For example, there are robots that are trained to harvest the fruit, and object detection can detect the fruit and help the robot approach the fruit and catch it. So in general, object detection solves two subsequent tasks. It localizes objects on an image and classifies them. Next, I want to talk about more technically what type of object detectors are there. The object detection task is divided into two groups, two-stage detectors and one-stage detectors, two-stage and one-stage. Two-stage detectors, two-stage detectors in the first stage get input image, and they output proposed regions where the object of interest can be. And for the second stage, for each region of interest, a neural network is applied, and it is decided whether the object is the object of interest or not. And in one-stage detectors, all that process is done with a single run through the neural network, and so you input the image to the network and get output the refined bounding boxes and their classes. And two-stage detectors instead of one-stage detectors are a little more have a little slow computation, but they have comparatively higher accuracy. But in recent years, both two-stage detectors and one-stage detectors are very comparable, and two-stage detectors started to get faster, and one-stage detector more detectors have more accuracy. Next, and as you can guess, to solve our problem, we need to use one-stage detector, because as you could see in the previous image where the technical specifications were, we use a Raspberry Pi plate in our drone, and in order to make fast computations, we need to have a detector that is working with high speed. And the most common one-stage detectors that are used are YOLO type of detectors, and they are, in general, they have this kind of architecture. The input image passes over the backbone. The feature maps are created with 3 different scales. The first scale is responsible for the objects that have higher that are bigger in the input image, and the last feature map is responsible for smaller objects. And after that, all these feature maps are passed to the detection head, and the detection head gives output the candidate bounding boxes. And now Nshan will talk about visual tracking part, the general overview of it.
Okay, so in practice, when using only object detection on a sequence of images, the images are just frames, and because there are some artifacts like motion blur, or sometimes light affects the scene, and basically the object that was detected in the first frame, it may not be detected in the some other frame. And just to make all this step a bit robust, and also to gain more speed in the computation, we decided to also use object tracking algorithm, and we're talking specifically about visual tracking. When the bounding box of the object is given in one of the frames, and on the consequent frames, the algorithm is just tracks the bounding box, basically keeps the bounding box in the image. And yeah, so again, there are 2 main approaches in this field. First one is using discriminative correlation filters, which basically the model gets 2 images. It goes through the backbone, extracts some features. One of them is the target image with the object that we want to track, and the other one is the search region where the object is located in a future frame. And then when we pass both of these images through the feature extraction module, we then apply correlation operation on the feature maps, and then we get a response map which contains information about where the object is most probably located. And then we just post-process the map and get a bounding box or even a segmentation mask if we want some more details. This is one of the approaches which we actually do not use. In our approach, we use deep Siamese networks, and the architecture is the following. Again, we have two images. This is the previous image processed, and by meaning processing, I mean we crop the image so that the object of our interest is located in the middle of the image, and the cropped image has spatial resolution twice as much as the object of our interest. And then again, both of the images pass through the backbone. We extract some features. We use only the the feature maps of the smaller resolution. We concatenate them, and then we pass these feature maps to the tracking head. And we get just one bounding box coordinates without any score. So we don't get a confidence score initially. Just a few notes. The tracking head is a simple head that consists of depth-wise convolutional layers. And also we have one dense layer at the end of the network, which actually we will get rid of in the future. But yeah, currently this tracking head consists of these layers. Okay, so just because we use a backbone layer, like backbone module, which is the same in both to solve both of these tasks, we decided to have just one unified backbone, and which will be used to solve both of these tasks, taking into consideration the limited constraints we have on the device. So this is what we did. We trained the model for object detection. So basically this part was trained, and then we froze this part, and we trained only the tracking head from scratch using only human cyclist data. Typically when people train visual tracking models, they use arbitrary models, objects, but we did not do that. So just a few details. So imagine this drone is flying. We have no cyclist detected yet. The object detection module is working, so the images pass through the backbone and the detection head, and then at some point we get a detection because we know the object is somewhere in the scene. And then whenever we have a detection, we start we start processing the image so that we can feed it to our tracking module, and this part starts working. And just because the tracking algorithms sometimes they don't usually have scores, some do, but the ones that we adopted for our solution did not have initially. We decided to introduce some measurement for certainty so that we could understand whether the tracker tracks the cyclist or it just went somewhere on the trees and stuff like that. So we basically incorporate some simple idea where we take the bounding boxes and we compute the cosine similarity between the visual appearance of the objects, and then we basically look whether the score goes down. Whenever it goes down the threshold, we start using the detector again, and then this goes on and on during the time when the drone follows the tracker. So we'll show some videos.
Okay, in this video you can see that at first the bounding box was green, and it was the part when the detection part was working, and when the sufficient number of consecutive frames were detected, the tracking part started to work. And as you can see in this video, the cyclist is normally tracked. Here also you can see not the part when the switch between the detection and tracking part is performed. This green part is the detection part. Okay, and of course not everything in our for the model is not for the model it is so easy to detect the cyclists, and sometimes the model confuses between person and cyclists and person and a bicycle, because it is not so easy to understand where it is a person who is riding a bicycle or a person alone. So we tried to solve this problem with different solutions. First, we added a lot of person data to our training data, also a lot of bicycle data, and it slightly improved our performance. But the more improvement we got when we applied multi-label training approach. By saying multi-label training, I mean that we trained with two classes instead of one cyclist class. We trained to detect people, person and bicycle alone. And when person and bicycle are in the same bounding box, it is classified as cyclist. And as we first started to solve the problem with only one cyclist bounding box, we didn't have much time to separately label this part and only this part for our problem, and we labeled this bounding box with both person and bicycle classes. I know that this is not the best solution, because with some part it can be hard for the model, but as we can see with our metrics, when we applied multi-label training, the average precision score was improved slightly, and when we also added tracking part, it got even better. And here you can see the evaluation on Raspberry Pi device. Without tracking, we got 20 frames per second, and with tracking, we got 25 frames per second result, which is really good for solving our problem. And here you can see a professional pilot, who is riding a drone like this that you have seen. But our vision is to solve this problem by computer vision, and yes, and we know that it will be not so easy, and only with object detection we couldn't solve this problem. We also need to have we need to add other parts. We need to add obstacle avoidance models, visual inertial odometry task we need to solve. We need to increase we need to get better object detector and tracker. So that's all.
I have a question about this scenario. Did you happen this scenario that there are like two cyclists and like drone kind of confused who to follow if they are going to other directions? What do you think would be the solution in this case?
It is one of our main problems that I haven't noted, but with at first catching the cyclists that you want to track. After that, in general, our model can track only that cyclist if they are not so hard cases that they are like in the same bounding box. If you talk with bounding boxes. But in general, our model can solve it. But in order to have better model, we need to also work on this part to identify the cyclists
Separately.
Yeah.
We haven't tested this part yet, just to summarize.
My question is, if you can imagine you have solved the tracking and detection perfectly, is it easy to control the drone? Because it needs to fly also, right? It needs to follow. Like this part is still another.
It's definitely not easy, and in order to make those stuff a bit easier, that's why we need to add more modules on our device so that we can avoid obstacles. Because basically, by saying
it's very hard. That's different. But like, imagine I'm on free.
if we assume it's just a field, there is no one, there are no trees that you may go and crash. The only thing is the latency by which you get detections and the speed of the rider. Both of the things are not issues for us because the drone itself can fly way faster than an ordinary cyclist, and we haven't encountered any issues trying this method in the field.
I see. So if it's a obstacle-free environment and you have the tracker and detector and cycles easily, normally you can just send the commands to your autopilot and it will.
Yes, but when we come back to the value this drone should make, we want to make a nice video, and in order to make a nice video, we don't want to just follow him or her. Yeah, it should do some. Yeah, like that solution. The main or one of the differences is the number of cameras that we're using. We just try to solve this problem with just one camera, and it makes the problem harder.
Did I notice correctly that you have 2 cameras, right?
We should have 2 cameras. At the moment, the frame that you have seen does not have the second camera, and I think we should also add another module for the recording the video, because we don't think that we can do all the stuff on that Raspberry Pi, recording high resolution video and also do all the other stuff. That's why we also, we consider adding another module that will just record the video.
Do you calculate also some automatic or trigonometric calculations to estimate the distance of the cyclist from you? Can you predict or estimate the real world coordinates of a cyclist, given the fact that you have your coordinates of a drone?
Just for the tracking part, we need the distance between the drone and the cyclist. We do it roughly by considering the bounding box size, and we get an estimate how tall the guy is or girl, and then we basically do those calculations to infer the distance between the drone and the cyclist, so that we don't crash or we don't lose.
Maybe you could use molecular depth estimation.
That's one of the things. When we say obstacle avoidance, we have molecular depth estimation.
So you're using
Currently we're actually working on it, and in the future we are considering adding that module as well.
Actually, one of the questions were verbalized, so I'll skip that. And the other question is, can you elaborate more why the usage of detector and tracking module is required in your solution? Because as I can see, like more sophisticated tracking algorithm can be enough for you. I mean, because you need to track specific object, right? You do not need to detect all the kind of objects, then start to try. And another question is, like, if you use object detection, you can use object detection and classic tracker. Why don't you do that? So,
First, for the part just using only tracker, okay, we have the guy, the owner of the drone, who needs to ride his bicycle, but the thing is that we don't have the exact visual representation. It may change through time, and if we had the exact bounding box, like his appearance, static appearance, we could use only tracking, but the real life scenario is more complex. He or she may have different.
I'm sorry, but you just need the initial, like.
Yes. We also don't want to make his life harder. We just want him or her to just release the drone, and then it will start to follow the cyclist, and there's no need to.
It's also when the occlusions occur. For example, in that example, the cyclist was behind the tree, and after that we need to also follow him or her, and so we need to redetect the cyclist.
Like, sophisticated tracker should handle that. I mean, if the object disappears and appears again in the frame, tracker should handle that. And like yesterday, the Hans talk, you should like see. There are many like advanced systems. Okay, and if I can, I would like to give another question relating to the FPS reporting. Yeah, it was in Raspberry Pi, right?
Yes.
I guess you need to do like a lot of optimizations or write a CPU code to run it in with this latency time. Am I right? And how hard was that to achieve this result?
We do have a CPP code to perform all of that. We just, for this, currently we only convert our models to Aerodynamics, and it gives this decent amount of latency for us, and we do not do anything else besides converting the model to Aerodynamics. And yeah, we just invest more time on the architecture of the model. And
So what happens if the object detection part fails? Does the drone start searching for the object, or just freezes?
at this stage, we basically the drone goes ahead, and it just keeps searching the cyclist in the frame, and we have this threshold. If there is no detections are found, just it will land.
But does it have a smart way to search for the object, or just goes up, down?
No, currently we just release it, and yeah.
More questions?
But can we have the drone back?
No. Speakers?